Good morning, dear students, and today we are going to solve May June 2012 2-1 paper. The course we are studying is Physics 5054, and my name is Ferhan Mazher. Today in this video, we will solve only the section A of this paper. It's a theory paper. We will solve section A of this paper. Section B of this paper, we will solve in another video. Let's start today's paper. Okay. So here we go. We have question number 1 is on your screen. Let me reduce the size so you can see the whole question. Okay. An astronaut standing on the moon throws a stone vertically upwards. The stone leaves his hand at the time t is equals to 0. The line on the figure 1.1 shows how the velocity v of the stone varies with the time t until at the time is 2 seconds. Okay. After rising, the stone falls. The astronaut catches the stone at t is equals to 6 seconds. There is no air resistance on the moon. Complete the figure 1.1 until t is equals to 6 seconds. Okay. Now we have to complete this graph. It's very simple. When you throw something upward, and the theory is that its initial velocity will be maximum, and as the body will be going up, when you its initial velocity will be maximum. When it leaves your hand in upward direction, its velocity is maximum, and when it moves upward, its velocity gradually decreases, and when the ball reaches at its top height, the velocity will become 0. So what is happening when the ball leaves your hand in the upward direction? The initial velocity will be maximum, and when it will be moving upward gradually, with the velocity will be decreasing, and when it will reach the maximum height, the velocity will become 0, and then it will start coming downward. When it will come downward, when it will start that journey in which it moves downward, its initial velocity will be 0. So on the top position, its velocity will be 0. And as it will move downward, its velocity will increase and increase and increase. And when it will touch the ground or touch the hand, the person who catches it, that moment its velocity will be maximum. But an interesting thing will happen. When it was going upward, the velocity direction of the velocity was upward. When it is coming downward, the direction of the velocity is downward. You see, the direction of the velocity has changed. So if you call going upward as a positive velocity, then coming downward will be considered as a negative velocity. Okay. So positive sign with the velocity or a negative sign with the velocity only means that the direction of your motion has changed. For example, when the ball was going upward, you call it positive. And when the ball is coming downward, you call it negative, because the direction of the velocity has changed. So on this graph, you see it's a velocity time graph. On the y-axis, the velocity is represented, and on the x-axis, the time is represented. The time is taken in seconds, and the velocity is taken in meter per second. So and when the time was 0, the velocity was 1, 2, 3, 4. It is 4.8 meter per second. And when the time is 2, the velocity is 3.8 meter per second. You see, the ball at time 0, the ball was thrown upward, and at time t2 second, the ball is still going upward, but its velocity is gradually decreasing. So he wants us to complete this graph. So put a scale on this line and draw this line in the same direction and continue it until 6 seconds. Okay. So during this, it will cross this x-axis, and I've done this on a paper. Let me show you that. So here you can see, I hope you can see, this is question 1A part. So here velocity time graph, here is the time axis. So at the 0, the velocity was 4.8. At 2, the velocity was, I think 1.6 something. It was 1.6, or at the 3, it will be 0. So this point and this point was given there. Let me see that again. Yeah. I think I said somewhere 3.8. It's not. It's 1 point. Uh, it will be 1.6. Yes, it is 1.6. By mistake, I think I said 1.8. Okay, so 2 comma 1.6. These 2 points are already given there. So join them with a straight line until t is 6. T is 6. It's a straight line. So you see, at time 3 second, it crosses the x-axis. It means here the velocity is 0. When the velocity of the body which is moving upward, you have thrown it in the upward direction, you have thrown the ball in the upward direction. When the velocity becomes 0, it means that the ball has reached the maximum height. When the ball which is thrown upward reaches the maximum height, its velocity becomes 0, and then it starts coming downward. So its velocity then starts increasing, and that velocity, because it is now you are moving downward. So if the upward going thing was positive, then the downward, when you move downward, that velocity will be negative. So that's why when it moved downward, you see the velocities are in the negative portion. The velocities are here negative. So I have completed this graph. That was the first part. Let's see what are the next questions. This was 1 mark question. Then he says, state the value of the time when the stone is at its highest point when that graph crosses the x-axis. At that time, the graph is, the ball is at its maximum height when the velocity is 0. That happened at time 3 seconds. Okay, so 3 comma 0, we write that. Okay, at t equals to 3, let me increase the size so you can see it much. At t is equals to 3, the body is at its highest point. Okay, so I hope you can see that. Okay, next question is on your screen. He says calculate the acceleration of the stone between the t is equals to 0 and t is equals to 2 seconds. You see it's a straight line graph, and he wants us to find out, it's a speed time graph, and he wants us to find out the acceleration of that body. If you have the speed time graph of a body and you want to calculate the acceleration, the formula is very simple. Just find the slope of that graph. At 0 seconds, the velocity, we know that velocity, and at 2 seconds, we know the velocity. So apply the formula of the gradient y2 minus y1 divided by t2 minus t1. y2 minus y1 divided by x2 minus x1, that is the formula of the gradient you must have learned in your mathematics. So it's a straight line graph. I can show you that. See, this is a straight line graph, and he's talking about these 2 points. Hey, at 0, 4.8 and 2, 1.6. So y2 minus y1 divided by x2 minus x1. Or if you want, directly use the formula of that, acceleration. We have the formula. Final velocity minus initial velocity divided by the time taken for that change. The final velocity, here I have taken because the whole line was a straight line, so its gradient throughout is the same. Here in this calculation, I have taken 3, 0 and 0, 4.8, and you can take 2, 1.6 and 0, 4.8 and do this calculation. The final answer will be 1.6 meter per second square. I have just calculated the gradient of that speed time graph, and the gradient of the speed time graph is equals to the acceleration of the body, and my answer is 1.6 meter per second, 1.6 meter per second square. Okay. Then he says a graph is thrown vertically upwards on the earth with the same initial velocity. State two ways in which the velocity time graph for this stone differs from the figure 1.1. That graph, they were talking about a ball which was thrown upward and it came back. This was done on moon, and on moon, we don't have atmosphere, we don't have air. And he says if we do the same experiment and same ball, but we do it on the earth, the circumstances are different. On earth we have a stronger gravitational field of the earth is stronger than that of the moon. And on the earth we also have the atmosphere, we also have the air. So when the body will be moving upward, it will be experiencing air friction, and when it will be coming downward, it still will be experiencing air friction, which was not present on the moon. And the value of the g on the earth is also larger than the value of the g on the moon. So when you draw this, when you will perform this experiment on the earth, the graph, if the speed time graph which you will draw will be a little different from the speed time graph which you have seen in the question. The main differences will be the body will reach to its maximum height. The maximum height reached will be less, and the time taken, for example, on moon it takes 3 seconds to reach the maximum height, but on earth the maximum height reached will be less, plus the time to reach the maximum height will be also less. And in less time the ball will be back to the ground. And plus another thing, the speed time graph on the moon is a straight line, and but on the earth it will be curved, it will be not a straight line. Straight line speed time graph you get, especially for the vertical motions, the straight line speed time graph you only get when you are in somewhere where there is no air resistance. But if there is air resistance present, like on earth the air resistance is actually present, then you will observe that the graph will be not a straight line, it will be curved. So let me read my answers. I have done this on a paper also. I hope you can see those answers. They are visible to you. Okay. C part, the graph will be curved due to air resistance, and graph will be steeper. And the graph will be a curve. You only have to write two aspects of that graph. Okay. Okay, we are moving to the next question. Question number 2 on your. Okay, dear students, now we are on question number 2, and the figure 2.1 shows a windsurfer sail and board. The total mass of the windsurfer sail and board is 90 kg. They travel at constant speed of 5 meters per second. A part is calculate the total kinetic energy of the windsurfer sail and the board. It's very easy, if you want to find out the total kinetic energy, you should know the formula. The formula for the kinetic energy is 1 by 2 mv square. 1 by 2 mv square, where m stands for the mass and v stands for the speed or velocity. We know the mass is 90 kg and the speed is 5 meter per second. Just put the values in that formula. Kinetic energy is equals to 1 by 2 mv square. So I've done this on a paper. Let me show you. Okay. So very easy. You see the formula, kinetic energy is equals to 1 by 2 mv square equals to 1 by 219 to 5 square, and the final answer will be 1125 joules. I hope you have understood. Okay, let's reduce the size so you can see the whole question. It was a 2-mark question. B part. Let me increase the size. The wind exerts a forward force on the sail. Explain in terms of the forces acting why the boat travels at a constant speed. Whenever something travels at a constant speed, uh, all the forces which are acting on that body, they are balanced, and the resultant force is zero. For example, in the case of this boat, the forward force exerted by the wind on the sail, that is balanced by the drag of the water or the frictional force of the water on the ship. And that frictional force is opposite to the direction of the motion of the ship. So if the forward force and the backward frictional force, they are equal in magnitude, but they are in opposite direction. So their resultant force will be zero. So when the resultant force will be zero, the acceleration will be zero, and the body will move with a constant speed. I have written this answer. It's a 2-mark question. I have written this answer on a paper. Let me show you that. So here we have forward force exerted on the sail by wind is equals to the backward frictional force of drag of water on boat. So resultant force is zero, acceleration will be zero, so body will move with constant velocity. I hope you have understood. The wind does work on the sail. Explain in terms of the conservation of energy why the total kinetic energy does not increase. Whenever the body is moving with the constant speed, the the energy which you provide is not used to increase the kinetic energy, because the speed is not changing, the speed is constant. If the speed is constant, the kinetic energy will be constant, it will not be changing. So the energy which you are providing during this time interval, or during this phase, when the body is moving with a constant speed, the energy you provide is converted into heat energy or thermal energy, and all the energy you provide is used to produce heat, because when you overcome the friction, your energy will be converted into heat. So you see, the energy, the work done by the wind is converted into heat. It is not being used to increase the speed, so the kinetic energy is not increasing. I have written this answer on a paper. Let me read that. Work done by wind on sail is used to overcome frictional force of drag of water with boat, and is converted into thermal energy which is lost to the surrounding. So the kinetic energy do not change. I hope you have understood. So here we go. A student measures the pressure inside a bicycle tire using a pressure gauge he has constructed. Figure 3.1 shows the apparatus he uses. The piston and rod moves along the smooth cylindrical tube. So here we have two bicycle tire. This is the opening which will be joined with the valve of the bicycle tire. Here we have a piston. Here we will have air. From this rod, you press it. The change in the length of the spring is proportional to the force. So when you connect it with the bicycle tire, so air will enter here and air will push this piston, and here we have a spring. So that spring will be compressed and this rod will come out. You must have seen this gauge. It is used in the tire shops to measure the air pressure in the tires of cars and motorcycles. The change in the length of the spring is proportional to the force applied to the spring. A force of 2.8 Newton compresses the spring by 2 centimeters. The student connects the pressure gauge to the tire. Air from the tire exerts a force on the piston. As the piston moves, the spring is compressed. The piston moves 10 centimeters to the right and then stops. Calculate the force exerted on the piston by the spring. You see, it's easy. When when the force is 2.8 Newton, the spring moves 2.0 centimeter. If the spring has moved 10 centimeter, how much is the force? So the force and the distance moved by the spring, that piston, they are directly proportional to each other. So you can use that directly proportional relation and you can find the length, the force which was applied. I've done this on a paper. Let me show you my working. Here we go. Force and distance, they are directly proportional to each other. When 2.8 Newton force is applied, the piston moves at 2 centimeter. So how much force is applied? We call it X. When the distance moved by the piston is 10.0 centimeters. So mathematically, I can write 2.8 divided by X equals to 2 by 10. Cross multiply it, make the X subject of the formula. So X will be equals to 10 into 2.8 divided by 2, and the final answer will be 14 Newton. I hope that you have understood. Okay. The the cross-sectional area of the piston is 3 expo minus 5 meters square. Calculate the pressure of the air inside the tire. So we know the force which was exerted, that is 14 Newton. And we now know the area of the piston, that's 3 expo minus 5 meters square. And we want to calculate the pressure. The formula for the pressure is force divided by area. P equals to F divided by area. Just put these values and you will get the pressure. I've done this on a paper. Let me show you that. So here we go. P equals to F by A, 14 Newton divided by 3 expo minus 5 meters square. And the final answer will be 4.7 expo 5 Newton per meter square. I hope you have understood this numerical. C parties suggest one change to the apparatus so that the piston moves a smaller distance when measuring the same pressure. You see, if you use the spring here in that diagram, what the spring here, if you use a spring whose spring constant has a larger value, or in a simple words, use a spring which is stiffer as compared to this one, then the piston will move the smaller distance for the same pressure. So use a spring which is more stiff as compared to this spring. Using a stiffer spring. That's the answer to the C part. D part of this question, each time that the pressure gauge is used, the pressure in the tire falls slightly. The temperature stays constant. Describe using ideas about molecules why the pressure falls. You see, you must have known that whenever this gauge is used to measure the pressure of air inside a tire, so when you attach it, so some of the air from the tire comes into this gauge. Some of the molecules of the air, they come out of the tire into this gauge. So you see, uh, the the number of the air molecules which are left inside the tire, they are now comparatively less because some of them have moved into the gauge and obviously they will be lost into the surrounding. So the number of molecules inside the tire, the air molecules inside the tire, that has decreased. Now, what will happen, because now there will be relatively less number of molecules of air inside the tire, so there will be less collisions per unit area. So the pressure inside the tire will be less as compared to the situation one. Now, another reason which people give, or you can also give, is that when you connected the gauge with the tire, so some gas enters into the gauge, and now the volume of that gas has increased, and because the temperature is constant, because now the gas is not just in the tire, but it also has come into the gauge. So the volume of the gas has increased and the temperature of the gas is constant. And if the temperature is constant, the volume, if the volume increases, the pressure will decrease. The reason is pressure of the gas and the volume of the gas, they are inversely proportional to each other if the temperature of the gas is constant. I've written this answer. Let's see what I've written. So some gas molecules enter from tire into pressure gauge whenever it is used. So number of air molecules in tire decreases. So frequency of collision of air molecules with walls of tire will decrease. So that's the reason why the pressure of the air inside the tire every time when you use this gauge decreases. I hope that you have understood. Here we go. A student slowly heats a sample of solid wax in a test tube. Figure 4.1 shows how the temperature of the wax varies with the temperature with the time t. So here you have a graph, and on the y-axis, the temperature of the wax is represented. On the x-axis, the time in minutes is given. Okay, so it's a heating curve. He said the question number one is state what is meant by melting point of a substance. Melting point of a substance is a specific temperature or is a fixed temperature at which solid converts into liquid. It's the definition. It's a 1 mark definition. I've written this on a paper. Let me read that also. Here we have. a specific temperature at which a solid will convert into a liquid. Temperature remain constant until all solid is converted into liquid. So as long as this process is going on in which the solid is converted into liquid, the temperature will remain constant. Thermal energy or heat passes into the wax throughout the experiment. Describe what effect this energy has on the wax between t is equal to 0 and t equals to 4 minutes, between t0 and t4. From t0 to t4, you see when you provided the heat, the temperature is rising. So when the temperature is rising of the solid, so basically its molecules, they have started vibrating more vigorously, and they might have moved a little away from each other. The solid will expand a little bit when heated, and the this molecules would have started vibrating more vigorously. Their kinetic energy would have gone up. I've written this on a paper. Let me read that. Molecules of wax vibrate fastly. Their average kinetic energy increases. They move away from each other. Okay, next question. Describe and explain what effect this energy has on the wax between T4 minute and T8 minute. So we'll go back to that diagram. You see, from T4 to T8, the melting process is taking place. You see the temperature remain constant from 4 to 8 minutes. So what is happening here? The wax is basically melting. So the energy which you are providing is not used to increase the average kinetic energy of the molecules of the wax. The temperature remain constant during this process. So the energy which you are providing is being used to, it is being used as a latent heat. It is being used as a specific latent heat of fusion. And it is used to break the intermolecular bonds. It is used to move the molecules away from each other. It is used to overcome the intermolecular forces. I've written this answer. It will be more clear. Wax melts, latent heat is provided, which is used to break bonds. Molecules move apart. So this is what is the energy is being used when from time 4 to time 8 minute. Okay. The wax expands as the temperature rises. It expands more between T8 minute and 9 minute than the T equals to 0 and 1 minute. Explain why. First thing you should understand is at time 8 minute till 9 minute, the wax is in the liquid form. And between time 0 and 1 minute, the wax is in the solid form. So when you provide them with the heat, when the wax is solid and when the wax is liquid, so when the wax is in the solid form, the expansion in the solid is less as compared to the expansion in the liquid. Liquids always expand more as compared to the solid. So from T0 to 1 minute, the wax was in the solid form, so it will have less expansion. And from T8 minute to 9 minute, the wax is in the liquid form, and liquid obviously expands more as compared to a solid. From T0 to T1, wax is solid, and from T8 to T9, wax is liquid. Solids expand less as compared to liquid. Okay. Figure 5.1 shows the electromagnetic spectrum, and you should remember that code before we go into the question. Ronald McDonald is very ugly except Gary. Ronald stands for the radio waves. McDonald stands for the microwaves. Ronald McDonald is, I stands for the infrared, is very visible light, ugly, ultraviolet, accept stands for X means X-rays. For Gary, Gary stands for gamma rays. So Ronald McDonald is very ugly except Gary. So radio waves, microwaves, infrared rays, visible light, ultraviolet, X-rays, and gamma rays. You should remember this password. Two components of the spectrum P and Q have not been named. State the name of the component P. So the P is X-rays. Component Q. The component Q is infrared. X-rays and infrared. All electromagnetic waves have a wavelength and a frequency. They all have changing magnetic and electric fields. State two other properties of all electromagnetic waves. All electromagnetic waves are transverse waves. Another property of all electromagnetic waves is they all travel with the speed of light in the vacuum. Or you can say they all travel with the same speed in the vacuum. All the electromagnetic waves, they travel with the same speed in the vacuum. I've written this answer. Let's see what is my answer. Okay. So for the A part, P is equals to X-rays and Q is infrared. For B, first, they all are transverse waves. They all travel with the speed of light in vacuum. State the component of electromagnetic spectrum used for satellite communication. For satellite communication, we use microwaves. Microwaves is the answer. A sound from an electronic organ, is played into a microphone, which is connected to a cathode ray oscilloscope. Figure 6.1 shows the trace on the CRO produced by the sound. So here, that trace. So this horizontal thing, that represents the time period. On the x-axis of the x-axis of the CRO screen, that represents time period or time, and the y represents the amplitude. So here the wave is completed. It took 0.020 seconds. So it took 0.02 seconds. The next wave also took the same time period. The next wave took also the same time period. The next wave also took the same time period. The next wave also took the same time to complete. So one very interesting thing before we go into the questions is that the time period of these waves is not changing. They all have the same time period. But one very interesting thing clearly is visible, that their amplitude is gradually decreasing. Amplitude is the height from the mean position, or the depth from the mean position, the maximum height from the mean position. The horizontal line marked L is the trace seen when there is no sound. Okay, so that L line, horizontal line, represents the mean position. State how figure 6.1 shows that the loudness of the sound decreases with the time. You see, in this diagram, the amplitude of the sound wave is gradually decreasing. The loudness of the sound depends upon the amplitude of the sound waves. So, because the amplitude is gradually decreasing, it means that the loudness is gradually decreasing. So I was telling you that if the amplitude, the loudness of the sound depends upon the amplitude of the sound wave, and you can clearly see the amplitude here is larger. The amplitude here is the amplitude is gradually decreasing. It means that the loudness of the sound is gradually decreasing. And how this is shown by the graph, its amplitude is gradually decreasing. I've written this answer. Let me show you that. Amplitude of the sound wave is gradually decreased. So this is how the graph shows that the loudness is decreasing. State how the figure 6.1 shows that the pitch of the sound is constant. The pitch of the sound depends upon the frequency, and frequency of the sound wave depends upon the time period of the sound wave. The frequency is equals to the reciprocal of the time period, because in the graph the time period is constant. So it means that the frequency is constant. The time period is constant, so the frequency is constant, so the pitch is not changing. So how does the graph shows that? Because the time period of that sound wave is constant throughout the trace, which is shown on the CRO screen. So from there we conclude that the frequency is constant. From there we can conclude that the pitch of the sound is constant. I've written this answer. Let me read that answer. Time period is constant throughout the trace. State what is meant by the frequency of a wave. Frequency means the number of waves passing from a point in unit time, or number of waves passing from a point in 1 second. Number of complete waves passing from a point in unit time is known as frequency. The time for one complete cycle of the wave in the figure 6.1 is 0.020 second. Calculate the frequency of the wave. F equals to 1 by T. Frequency is reciprocal of the time period. So just put the value of the time period in that formula, you will get the frequency. Let me show you my working. The time period given is 0.020 second. F is equals to 1 by T, 1 divided by 0.020, and the final answer will be 50 Hertz. I hope that you have understood this question. Determine the time taken for the amplitude of the trace in figure 6.1 to decrease to half of its value, half of its initial value. Let's go back to that trace. So here, look at here. So it's 10, 11, 12, 13, 14. So here the amplitude is 14 small squares. So half of this amplitude will be 7 small squares. 1, 2, 3, 4, 5, 6, 7. So here the amplitude has become half of its initial value. The initial value of the amplitude was 14 small squares. And here the amplitude is 7 small squares. So the amplitude here has become half of the initial value of the amplitude. So what's the time here? So this is 0.02. So this will be 0.04. So this will be 0.06. So at the time 0.06 second, the amplitude has become half of its initial value. Initial amplitude was 1.4. The amplitude number 2 is 1.4 divided by 2, 0.7. And from the graph, I looked where is the amplitude 0.7. And from the graph, I came to know that at time 0.06 second, the amplitude was 0.7. I hope you have understood this. Figure 7.1 is the circuit diagram of a circuit set up by a student. The student uses 3 cells, each of electromotive force EMF 1.5 volt. The cells are connected in series as shown. So here we have 1, 2, and 3 cells. State the name of the component P. This component P is called light emitting diode. LED, light emitting diode. The next question is, state what is meant by electromotive force of a cell. EMF of a cell. EMF of a cell is the energy provided by the cell to move unit charge in a closed circuit. Or you can say, it is the work done by the cell when unit charge flows through the cell. Or you might also define it like this: the amount of any other form of energy or amount of chemical potential energy converted into electrical energy when unit charge flows through cell? I've written this answer. Let me show you that. Work done to move unit charge around the closed circuit by source of electricity or electric energy, source of electric energy. You know, the formula for the EMF is work done divided by charge. EMF is equals to work done divided by charge. The student expects the reading on the voltmeter to be 4.5 volt. The actual reading is 0.2 volt. Suggest two reasons why the voltmeter reading is much less than 4.5 volt. Look at this diagram carefully. First of all, look at the arrangement of the cells. So this is cell number 1. Its negative is connected with the positive of the cell number 2. But the negative of the cell number 2 is connected with the negative of the cell number 3. This cell number 3, it is connected in the wrong way. Its positive should be here and the negative should be here. So this third cell is cancelling this second cell because they all have the same EMF. So these two cells are basically cancelling each other because here you connected negative with the negative. So now only this cell is good. Only this cell is providing the electric energy. So only 1.5 volt EMF is provided by this battery instead of 4.5 volt because the cell number 3 has been connected in the wrong way. The second reason is that in this circuit, there are two resistors. One is a lamp and the other is a light emitting diode. So some voltage is taken used by this lamp and some voltage is used by the LED. So the EMF which came from the battery is not shown by this voltmeter. This voltmeter is only showing the voltage drop across the lamp. But the EMF has been divided between the lamp and the LED. So the voltmeter reading will be less than the EMF of the cell. I've written this answer. I've written the answer. Let me show you that. One cell is connected in the wrong way. That's the one reason. And the second reason is some voltage is dropped across LED. In the space below, draw three cells connected in parallel. Just a very simple thing. If you want to draw cells in parallel, let me show you here. You can see I have drawn this diagram. The cells, the three cells, they are connected in parallel with each other. We have connected the positive terminals with each other and the negative terminals of the cells with each other. And then you can take out the connections. So this is how you connect the three cells parallel to each other. State one advantage of connecting cells in parallel. You see, when you connect the cells in parallel to each other, the cells their life becomes longer, they last longer. If one of the cells die, the other one will keep on providing the electric energy. So I have written the answer. You only have to give one advantage. Cells last longer. A magnet is placed on a bench as shown in the figure 8.a. End P of a rod is held above each end of the magnet in turn, as shown in the figure 8.1b and in the figure 8.1c. One end of the magnet is lifted off the bench in both cases. So you see, when I brought this rod, the P end of the rod on the north was attracted. When I bring the P of that rod near the south of the permanent magnet, the south is also attracted. So just what material the rod is made from? This rod is made of some kind of magnetic material. So you might say it's made of iron. We have written the answer as soft iron. Explain how the rod lifts each end of the magnet off the bench. You see, it's a soft iron. When you bring this P near the north, due to magnetic induction, here a south pole is induced and here a north pole is induced. So on P, a south pole is induced. This iron, when it comes near this permanent magnet, this iron also starts behaving like a magnet due to magnetic induction. So on P, S pole is or south pole is induced. So this south pole and the north pole, they attract each other. In this diagram, when you bring the P near the south, due to the magnetic induction, this iron, soft iron, also becomes magnetized temporarily. Here a north pole, on the P a north pole is induced. Here the south pole is induced. This north and this south of the permanent magnet, they start attracting each other because the opposite poles attract. Question was, explain how the rod lifts each end of the magnet off the bench. I have written this answer. Let me read that. Due to magnetic induction, when P is near North Pole, it becomes South Pole. And when P is near South Pole of bar magnet, P becomes North Pole. Opposite poles attract, so that's why the permanent magnet is attracted to the soft iron. I hope you have understood the description. Figure 8.2 and figure 8.3 shows views of a wire carrying a current downward through a horizontal board. On figure 8.3, draw the magnetic field due to current in the wire. So in the figure 8.3, you can see the wire is represented with a cross. And when a wire is represented with a cross, it means that the current is going into the page or into the screen. So we can apply the right hand rule for the straight conductor. So if I apply, this is my right hand, if the current is going into the screen, the curves of my finger, they show the magnetic field. So when I look from here, they are clockwise. If you hold the conductor in your right hand in such a way that your thumb is pointing in the direction of the current, then the curves of your finger, they show the direction of the magnetic field lines. And when I applied the right hand rule for the straight conductor on this conductor in figure 8.3, I came to know that the direction of the magnetic field lines should be clockwise. So I will draw here concentric circles. Okay. And I will put arrows on them to show the direction of the magnetic field, and those arrows should be showing clockwise magnetic field lines. I have done this on a paper. Let me show you. In this diagram, you can see that we have drawn concentric circles around that conductor. And on those circles, we have put arrows, and those arrows shows that the direction of the magnetic field is clockwise. Another interesting fact is that near the wire, the circles are closer to each other. And as you move away from the wire, the distance between consecutive circles gradually increases. The magnetic field is stronger closer to the wire. State how the magnetic field lines indicate that the field is stronger. Wherever the magnetic field is stronger, the magnetic lines will be closer to each other. If the magnetic field becomes weaker, in that region, the magnetic lines will be far away from each other. So I have written this answer also. I hope you can see that. Near the wire, the magnetic field lines are closer to each other, and this shows that the magnetic field there is stronger. So wherever the magnetic field is stronger, the magnetic lines will be closer to each other. So my dear students, now we have reached the section B. The section B of this paper we will do in another video. Today in this video, we have only done the section A of this paper. Today, we have done May-June 2012 2-1 paper. It's section A in this video. The course we are studying is Physics 5054. My name is Farhan Mazher. I hope that this video is helpful to you and it will help you to improve your grades and your concepts and your answering skills of physics. Thank you very much and have a good day. God bless you all. Thank you very